Hi, thank you for attending this webinar. First, you may wonder why it is time sequenced instead of time series. Indeed, we will talk about time series data, but there is a possible confusion between typical time series analysis and what we will discuss here. Usually, when we refer to time series analysis, we are to forecast some future values based on historical records that are time sequenced. For the subject today, we prefer not to lead you that way and have concepts like ARIMA or SARIMA occupying your mind right away. So, my name is YC Lee. I'm an AI project consultant with Scientific Formosa here in Taiwan. I have been a consultant for the past 10 years. Before that, I have taught or worked in US first and then in Taiwan for more than 20 years. Here we will refer to a popular data set that has been experimentally obtained with a hydraulic test rig. The label indicating whether the internal pump of the engine is leaking or not is provided for all the 2,000 plus hydraulic engines. And each engine went through a test cycle of 60 seconds. Some sensors provide 3 readings per second, while others have only 1 reading per second. And that's why we see some missing value entries here. As some of you may know, if we were to take the data sets as is to train a model directly, then first, the number of attributes will be too many. And then the result won't be good either. But if we were to visualize these readings as waveforms, we might be alluded to deriving some attributes that are more interesting and useful. Of course, we need to first normalize each column of the sensor readings for visualization like this, and also for subsequent model training and tuning. Let me first provide some background information for the whole series of tutorials we have compiled here. This webinar is the second tutorial. We have prepared these 6 tutorials mostly from different data prep perspectives and compiled end-to-end scenarios to demonstrate these preprocessing techniques. What are the motivation and the objective then? We know RapidMiner is powerful and easy to use, yet we continue to see some of our customers struggling to become better at RapidMiner platform. And one of the key reasons, as we came to realize, is the lack of creativity and instinct that blocks the users from problem formulation and solutions. Oftentimes, we do not know what attributes we can and should have in order to formulate the problem properly. By problem definition in this context, we mean there would be a clear problem statement that includes what attributes we should prepare and get them ready before training a model. Therefore, in order to leverage RapidMiner platform, our objective here are to highlight those concepts and techniques associated with data set transformations. Such knowledge will come in handy when we are presented with high-level yet vague business problems. It helps us to come up with different alternatives for problem formulation and the formats of the data sets that are required for model training and tuning. An important reminder here is that there are prerequisites for these tutorials. Though the order of these 6 tutorials is recommended as shown here, they can be taken in any order. But we need to be familiar with the usage of the tool itself first. It is okay that the number of operators we have practiced is still limited, but these terminology should be very clear to you. As you can follow these moving circles, these are the functionalities that you should be fairly clear and confident about. Now let's come back to today's topic. RapidMiner have strong coverage on manufacturing industries where we need to deal with multi-modal sensor data and the business objectives like downtime, throughput, and yields. Two RapidMiner webinars are quite interesting. The first one emphasizes the basics of data preparation for modeling, including windowing, approximation, and transformation. The second one emphasizes the trade-off between end-to-end processes that are either aiming at better performance metrics or shooting for operational ease or adoption by the floor. The instructors are brilliant, and the experience that they have provided many interesting ideas. I would recommend you to watch the recordings of these two workshops. So we have a classification problem here. We know that the time sequence data is not a good candidate to throw right in for model training. Instead, we would like to derive additional attributes that may describe the objects in a better way. Here, we talk about the concept of object profiling, something we have kind of touched upon in the first tutorial. Since we are to predict the internal leakage of an engine, we want to create a profile for each engine that would characterize its health in a better way. Okay. Conceptually, we will be extracting features from the corresponding waveforms. We may need to deal with missing values first, and then extract peaks, summaries, or approximating coefficients. We can get the data set from the UCI repository. That's UC California in Irvine. 17 sensors of the test rigs are shown here. For example, FS1 is a volume flow. And the data set includes sensor records and the labels for leakage, as we mentioned earlier. Allow me to call, first of all, this type of problems implicit time series problems, because we are not explicitly forecasting a trend composed of future values. We have combined the material from the two RapidMiner workshops with our own twist, and we will talk about two approaches here. The first one is centered around the concept of object profiling, something we talked about, right? And it uses the whole set of data to derive attributes that describe the engine status. The second approach is considered more pragmatic, as it uses only the first 10 seconds of sensor records to forecast the value of a specific sensor attribute for the next 4 seconds. So it then uses these forecasted values for leakage classification. It will be interesting to see the trade-off in between the two approaches while learning about how to build up the RapidMiner process. So this is the repository we used in our hands-on workshop. Well, we will go through the process for these two approaches. First, we show approach A. Based on the full profiling, the result is not bad indeed. And then we run the approach B to introduce a similarly more intuitive and a straightforward process for the lead of the shop floor. It picks up some salient attributes and try to forecast its values, right? Just during the first 10 seconds, and then predict the leakage based on these forecasted values. The resulting performance, as we will show later, is only slightly worse, but may be useful in operation, as the model is simpler and quicker, being able to predict the leakage soon after 10 seconds into the test. Okay. Now, the third part of this tutorial actually takes a step back, and the question if using the actual values of the same salient feature will even do better than the forecasted values. Okay, even though the trade-off is that if we use the real value, then we have to wait for 14 seconds instead of 10 seconds. This tutorial as a whole will give us the time series functionality a fairly comprehensive coverage and exposure. Okay. So the very first step is to group the records to individual engine. Okay. With a loop operator, we can focus on what we would like to do about a specific engine. For example, here we just click on the specific example set for engine 1462, and we will see all the records, supposedly 180 of them, and for 60 seconds, right? Now, before we can run the normalization, we need to fill in some values for the missing values. We can use different kind of method, for example, linear interpolation. Okay, so once we do that, we can do normalization and to see the waveform of all the sensors. Right. Now, for example, we can then run the aggregation operator with average functions as a default. Okay, and at the end, we now have the average value of each sensor to form a profile record for the specific engine. Now we are about to throw the data into AutoModel for processing, right? But before that, we need to complete the simple process, as we need to append all the profile records together and join with the labels, the leakage label. Okay. Now we are ready to run the AutoModel. We run 3 algorithms here: deep learning, decision tree, and gradient boosted tree, just as example. Okay, so quickly the result will come out, and now we can find out the accuracy. Looks okay. Sensitivity, recall, precision, and F1 measures. All right, and deep learning looks the best, and the decision tree has the worst precision that drags its F1 measure further behind. Okay, but anyway, this is just a simple try and a simple example. Other than the default average values of each sensor attribute, we can do a lot of other things. In particular, we can look for more sophisticated ones that may describe all the waveform better. Now, for example, one sensor has interesting peak information, while the second one seems to fluctuate along the time. How can we derive attributes to catch both of them and other patterns? Here we will show 3 different kinds of derived attributes, just for example, right? But for completeness sake, let's talk about replacing missing value first. And we have 2 consecutive replacing missing value operation here. The first operator, as highlighted, does the linear interpolation, while the second one uses next value just to catch up the missing value at the beginning. Okay. Now, for the first derived attribute, we are looking for the coefficient of the approximating polynomials. Here we set the degree as 2. That should come up with 4 coefficients. Okay, so you can see that is coefficient 0, 1, 2, and a discrepancy. Okay, and The second one is to extract the information about peaks. So you will see for sensor CE and then later sensor CP, the corresponding peak information will be extracted. And the third one is interesting, okay, is to run some aggregations, but unlike earlier, earlier first one and first two, we do the whole window, right? But here we break the sequence into smaller windows, and for each smaller window, we do aggregations. This is interesting and powerful. I will show in the next slide. Okay, but before that, once we have all these three kind of derived attributes ready, we combine them and run the correlation, and we can see the order of weight as shown here. Of course, engine ID is something we should have excluded at the beginning. It's useless for training. And then after that, you can see the average value of S1 or whatever, okay? Okay, now let's take a closer look into the process window as needed for the third kind of derived attributes in the previous slide. Okay, as specified, it is to first break the whole test cycle into 7 seconds, that is 21 records sub-windows, right? And as specified here, 21 is a window size, and inside this process windows, if we run a simple operator named extract aggregates and specify the aggregates we like, such as mean, standard deviation, okay, so we should come up with 8 records. As you can see from the time step, each spans about 7 seconds, and the last one is incomplete, so we have only 8 records here as a result of the second, number 2 here. Now in the number 3, we generate ID for each record. Remember, each record is now stands for a sub-window. Now we need that because at the end we will use pivot operator to flatten up all these 8 records, and the system will generate some attributes for different columns, and this ID will be important, right? And then also when we are done with this whole process, we need to attach the final record with the engine ID. And where can we get that? The loop average macro as an engine ID shown here is the perfect candidate. So we just add an attribute called engine ID to this record. So finally is the pivot operation. Now this pivot operation depends on how familiar you are with them. You may have to spend some time to play around, but it should be okay. The group by attributes or column group attributes and aggregate attributes is similar to the aggregation we've done before, and just play around with it and look at the input and output and check carefully the attribute value that generate. So as a result here, you should be able to see that the roll number and the engine ID. After that is all this aggregates. We just check it out, okay. Now we go through what kind of time sequence data preprocessing steps, and that is critical, and we should practice more to make sure we understand those steps, right? Now, to complete this flow, the rest looks easy now. Okay, we can just set the row and send it to the cross-validation to train some model and see the performance, right? And some of you may have noticed that we actually generate 386 attributes. That might be a bit too many. And some even may ask whether all these attributes are useful or helpful. Will they happen to kind of defeat the purpose and mess around all the training process? So instead, you can use the top 10 attributes with highest weight, right? And here we use the 380 attributes and set the label, and then go through the cross-validation where we split into the training and validation phase, right? So as you can see here, we have decision tree is the currently running, and but we can also link to the deep learning or GPT, right? And okay, now let's look at the result. This confusion matrix from the cross-validation. Okay, let's quickly go through them and make sure we know exactly how these metrics are computed. First of all, the accuracy should be no problem, right? But not sure if any of you have really examined the count in the confusion matrix of cross-validation. If we add up all this number together, actually it is the size of the training data set. The reason being that they just added up all the 5-fold validation, all the steps that range cover through all this training data, right? And they will be added up together. And the deviation of the accuracy comes from this 5-fold. All right. Now, for true negative, false negative, false positive, and the true positive, the negative case here is a leakage, right? And the positive is no leakage. So for sensitivity, recall, selectivity, here we are talking about the percentage of those true no leakage that have been predicted no leakage. And then for precision, the true no leakage case out of all those got predicted as no leakage. And they are actually pulling each other. And the good trade-off is harmonic count, that is the F1 major. They just balanced out a little bit to put some emphasis on precision and some emphasis on the sensitivity. And actually there's a beta value. Here the case beta value is 1, right? The beta value is to decide the weight of precision over sensitivity, or the other way around. Anyway, we also ran this cross-validation with the 10 attributes with highest weight. And you may be interested to look into the performance comparison here, and may spend some time to run with some different options. But anyway, let's stop here because our main purpose is to illustrate how those derived attributes can be processed. Okay. Now, we mentioned that cross-validation is actually just a part of training. So the performance actually is looking at within the training data. So we would like to do this classification with something split it out first. So we have the split operator beforehand to do a 7-3 split, and only use 70% of the data for cross-validation, and the rest of 30% data, then do the final test. So that will be independent enough so that we can be less influenced by the training process, right? Okay, so as the same thing here, we run some, and then again we come up with this confusion matrix, and you can see performance of using all 386 attributes or the 10 top attributes. Comparison here, just I put all them together. On the top is a cross-validation, right? And then on the bottom is that after the cross-validation, we do an independent test. Of course, we had a split data before the training, before the cross-validation. So you can see that probably some of you can find it out. Some model and some setting, some configuration is more robust and is less overfitting. Okay, but anyway, So sorry to rush it a little bit, but let's pause and think here. Now, the challenge we have is to detect the engine leakage, right? And with 180 timestamp records of 18 sensor readings or 17 sensor readings, right? It seems to be a hard problem to tackle. But we have achieved a relative good performance, either by all 386 attributes or by the top 10 weight attributes. Now, how did we get here? We use approaches as object profiles with derived attributes. These attributes are either approximating coefficients, peak characteristics, and sub-window statistics, right? So are we home free? Are we done? Probably not, okay? As far as the domain expert or the flow manager is concerned, the prediction model may not be intuitive or pragmatic enough. You heard similar things when people are being asked to take a deep learning model or a gradient boosted tree model. Usually their performance is pretty good, but the domain expert will just say, well, the model is not intuitive enough, or it's not what I can comprehend. But anyway, so just as an engineering practice, we can possibly look for some straightforward and faster alarming mechanism, right? So long as it is reasonable and in sync with the flow wisdom and the practice. Probably it's at the expense of slightly lower performance. So that's what we will do with the next approach. So now we're done with approach A. Let's move to the second part, approach B. Right. Here, as mentioned earlier, we would like to see if we can simply use the first 10 seconds of records and to predict the next 4 seconds for we call it salient attributes, right? Then use these forecasted values of the salient features to do the classification. That is to determine whether the engine is leaking or not, right? And then basically they will be able to be quicker, and hopefully if this works and sounds more practical and intuitive and human interpretable, so that will be accepted by the flow, the operation, okay? But let's see if indeed this is the case. So we have two questions here. First, which attribute is more salient than others? This is a term used in pattern recognition in old days. In the workshop reference here, the lecturer highlighted a decision tree that should seem to do okay. Now, I think they look at this, for example, decision tree or the forest, and then see that FS1 is always the leading attributes that start with the classification, right? Now, note that the attribute we are using is average FS1 mean underscore 9. It is an aggregated value, but let's look at the distribution of FS values first, right? There seems to be a good separation, so we can zoom it in, and indeed there are some separation, but the separation may not be as good as 99% or even just 95%, right? But anyway, we will ask this question, and if instead of waiting for the full test cycle, 1 minute to complete, can we detect the leakage easier and faster? Specifically, can we use the sensor data of the first 10 seconds to predict the FS1 values of the next 4 seconds and immediately alarm a leakage by a simple decision tree? Actually, the flow lead, the domain expert, may ask questions like this. And I think it happens often when a data scientist is talking with the domain experts. Okay, so let's give it a try then. So there's a proposal to say, can we use the first 10 seconds, that is 30 records, to predict, to forecast the next 4 seconds, that is 12 records. Okay, now we will try to derive some meaningful features as proposed in the previous slide, right? Now, if you think about this, this is actually a more complicated flow. Why? Because this is a two-stage classification problem. The first stage is to forecast some values. The second stage is to use the forecast values to do classification, right? Each stage by itself is a learning process. So you have to do training, validation, and testing. Then use the tested model to move on to the next stage, right? Anyway, this, however, may look like complicated in terms of process and flow, but on a high level, that might be easier to explain as we try to talk in English in the previous stage, in previous slide. So who knows, that might be more acceptable by the domain expert, right? Anyway, here our first priority is to understand that if we want to derive some attributes to do forecast or to do classification, what can we do in this case, right? So as you can see that, again, we join together the test data and the sensor data, then we group into collection, and inside the loop collection, we will deal with each engine one at a time, right? And then at the end, each engine will have a record describing their profile and append them all together, and we'll fill out a necessary one and goes to the build model, right? So inside this loop, we should be able to cover the process of deriving the necessary attributes to do the forecast of FS1 value. So first of all, we should have a sub-process to label this FS1 as a value we want to forecast, right? So as you can see here, we'll set the row and then generate ID and do some renaming, right? And then select the attributes here. Okay, now that need to be done, but it's okay. Now the more important part is this number 2 here. It's a process window. It's very much like what we did earlier in the approach A, right? So here this window is rather small, so we may as well just choose one single window. The size is 30, right? Remember, we used the first 10 seconds of records, 30 records of them to do this processing, right? But we are to forecast 12 values, so the horizontal size is 12. Now remember, this is the multi-step forecast. It's not just forecasting a single values, right? And inside this process windows, we can have a number of processing flows to derive the attributes we want, right? Again, it looks similar to previous one. Inside this window, we do extract aggregates, so you get some of these aggregations out right away for that window. And then we can start filling in some missing values and then to move into some smaller windows. Why we do this smaller window of window size 3 is actually we will try to see if for the smaller window it will come out with a better approximating coefficient to describe the waveform, right? So inside this process window, what we do is just extract the coefficient for the window size of 3. Then we can do it rather quickly. And then we also need to make sure we have engine ID or the whatever that's to attach to the resulting record so that all this record will not be lost and somewhere knowing that without any idea what particular engine that record belongs to, right? So This looks complicated, but I think you can play around with that and you can see how that is done, right? So now we have the forecasting models. This is the first phase of this whole process, right? And this cross-validation as usual. But here, you notice that we are forecasting 12 values instead of just one. So in RapidMiner, they have particular operator called multiple horizon forecast operators. And then for the performance, this is also have the corresponding performance operator. And inside the performance there, inside it, you choose whatever performance operator you are used to have. And over there, you can pick up the particular metrics you like to look for. So for this forecasting problems, you may look at this mean square error, absolute error, things like that. As for this multiple horizontal forecast, again, we can say, for example, and I will choose the attributes by weight, and then I run some models like gradient boosted trees, right? Okay, now we have the training data ready for forecasting. In the RapidMiner workshop, they choose such a split. Okay, the first 1,999 engines for training and 136 for testing. That might be a bit unbalanced, but anyway, we will follow along so that we can do some comparison later, right? The forecast results look like this, and you have at the right have some list of the actual FS1 value or the predicted FS1 values, and of course its record should be associated with the engine, the leakage status, and the engine ID and the timestamps. Okay, so you can see that for each engine there are only 12 forecasted values, right? Now, if we try to show this distribution of all these values, remember the green and blue are what is the actual FS1 value we showed. Blue is for leakage, and the top green is for no leakage. Now, with what we just forecasted, this brown or red case is the predicted FS1 value for leakage case, and black on the top is for the no leakage case for the FS1 predicted value. Now, actually, we have for each engine, we just have 12 values here, and the x-axis has 12 values there. And just because in order to see the distribution, there's smearing a little bit of this data points and spread them out. So as you can see, each cluster is centered around a particular time, right? The red one here indicating the number 6 forecast value. That is the last one for the second, if you will. And probably we can talk about this within the whole cycle is the 12th second. Now, if you zoom in, you can see the difference between the actual FS1 value or the predict FS1 value. And you might say, well, look like indeed the predicted value is the better indicator, and it seems to be more discriminant, right? So as demonstrated in the webinar, they've shown the process like this, and we just follow along, and we come up with confusion matrix like this. And probably limited by the remaining time, this webinar just stopped here. And then they pick the FS1 value at the interval, at the record 6. That again is the end of the 12 seconds. You use a predict value and just use a threshold value to say whether the engine is leaking or not. Okay. The performance look good, but the number of test records, just 136 of them, may not be representative enough. So that might be run out of time, but we do have some time here. We would like to take a closer look into this approach to maybe making it more formal and more rigorous. But of course, we run into danger. Maybe just try to make little things a big stuff. All right, so if indeed, we like to see if indeed the predicted FS1 values are better attributes. How about the actual FS1 values? At end of 12 seconds, might be they don't perform as well as a predict value. But how about we take the whole 4 seconds to do the classification as a second phase? How would they come out, right? So then if you want to practice more, you can see if we use the variable curve or we use the approximating coefficient of the curves, which one would be better? Okay, the workshop from RapidMiner reminds us the importance of model acceptance on the manufacturing floor, in addition to performance metrics. It is just unfortunate that the workshop ran out of time to get a closer look at the end result. Here, we will try to get a closer look to agree or disagree, right? And this approach, if you think hard, as we mentioned earlier, is not that trivial. It's a two-stage prediction problems. The first stage is to forecast some values. Then the second stage will use the forecasted value for predict the final prediction, right? But they think about that for each stage, we need to do training, validation, and the testing. Same thing for the second stage. So technically, in the first stage, we should split the data first, save some data for the next stage. And then we also save the model training by the partial data, right? The 70%, 50% of them. Now, into the second stage, we will first take the test data reserved from the first phase and then run through the model again, resulting from the first phase, and generate all the forecast data. Now, we need to split them again, reserve some for the final testing, and the rest go through the training. And then we also store the model there, right? So at the last stage, we can do the performance test, right? So with the first stage, we have gone through them earlier. So we talk about the second stage. Here, we have to detect the data, the test data reserved from the first stage, and try to forecast all the FS1 values. That actually can be simply done, okay, easily done. But here, we just try to open up some of this closer look, as I mentioned earlier. First, the loop attributes operator here is kind of tricky. Now, as some of you may know, that is, you use the prediction model to predict some value. Those values are not regular attributes. The predict values are special attributes. So we have to turn them into the regular attributes for the subsequent training purpose. So here we set the labels and the prediction value as a regular attribute. Now move on to the next sub-process. This is where, just for demonstration purpose, right? I will prepare the attributes. If we postfix with -p, meaning these are predicted value. Remember, we want to compare them to see if the actual value is actually better than the predict value. So we also prepare attributes and name them with postfix underscore a as actual values, right? And then at the end, we will do the selecting attributes as we will go with any specific configuration, pick up the corresponding attributes to do the test performance. Okay, so for example, here the second step, we set the row. As you know that now the row is the pump leakage, right? And the sub-process here is we will try to pick up the actual values or predict values. That can be done if you have the forecast value ready already. So now we can set the whole things up now for performance comparison. Right now we can disable the first phase because that has been done and we don't have to repeat them for every different configuration. By configuration, I'm talking about whether we are using actual value or forecasted value, or whether we are using the values themselves or the approximating coefficients. So you come up with 4 different configurations, and we should be able to see the difference between these configurations. So then below is this what we just shown for the second phase flow, right? And then the set macro here definitely will pick up a specific configuration for us to run. For example, here I run this, and then say I want to use approximating coefficient of FS1 values instead. And so we will actually go into something and then run some similar exercise we did before. Now this is the 3rd time we try to run approximating coefficients. So you should be fairly familiar with the typical step we can do. So may as well just use it as a practice to understand them, right? And again, the flow looks similar. At the end, we are ready to do some performance comparison. Okay, so for example, I quickly run all the 4 configurations. We come with a number like that, but this, of course, can be said better by a chart here. So as you can see here is that these 4 different kind of configurations, right? We use the values themselves, whether it is actual FS1 value or forecast FS1 value, or we use the approximation to approximate the actual FS1 value, or to approximate the actual the forecast value. Remember, we have 12 values to do it, and so we just don't want to see if just throw the 12 values as the 12 attributes. Sometimes we use approximating coefficients to see whether that will improve the result or not. So again, down there we show the accuracy, recall, and the precision and F1 measure. And you probably can see that the approximation is a little bit too much. And we probably make an end hole as a hill, right? Anyway, it's interesting to see that, and now we will just here pause again and think again. So the challenge we have here is that a lot of time we need to communicate with a flow manager or domain expert about the proposed leakage classification model and gain the trust. Sometimes it's just hard to convince them that a more powerful model is doing the right things or not, because it's their call to accept the model, right? So what we have achieved is that we run different configurations, and these approach, of course, whether it's done in 10 seconds or 14 seconds instead of 1 minute, right? And we'll focus on the FS1 values, and we come up with the accuracy. The range is, for example, here, the accuracy is from 95 to 99, right? So using actual FS1 value actually runs pretty good and predict FS1 value, whether it's use the values themselves, approximating coefficient looks about the same. On the other hand, if we use the actual FS1 value, and it probably fluctuates a lot, and when you use the approximating coefficient, with degree 3, the accuracy drops. Right? So how did we get there? We actually build a forecast model and train that first 30 records, right? And then we classify. Again, the whole process, if we make it complete and rigorous, it's by no means easier than the approach A, right? But in terms of communicating with a domain expert, there's a difference between the language they use, between the concept they can accept. So are we home free now? Right? This second approach is somewhat pragmatic, as we know. The findings are definitely arguable, not just presumably arguable. Nonetheless, we did see that using the predict FS1 value is different from the using the actual FS1 value, right? But to get to this point, the end result may not be as important as a process we have run through. And when we run through them using all different techniques that probably are still quite fairly complicated as you're concerned, right? As far as you're concerned. But I think just take a little bit look into the examples, and you should see and should be able to find out the basic step that you can do in order to derive meaningful attributes from the windows or the sub-windows, right? So the key concept and the preparation techniques here we are talking about building the object profiles, and then we derive the useful attributes from the embedded time sequence data. Now we also think about the trade-off between that and some easier or faster approach. Now, here we are actually getting down to the case of multiple horizon forecast of specific attributes. Right? So what we learned, just a quick review of the operators we have run through. Again, we do this group into collection and loop collection, and we append the result together, right? And we use the process windows where we can plug in the extract coefficient or other things inside it, and we can extract the peaks, we can extract the aggregates, right? Now we can also do the join to finally join everything together, right? So as for append, you probably learn some difference between append the superset or the merge attribute and the aggregates and the pivot. That's a lot of important operators for you to get the basic idea and be familiar with them. Okay, thank you very much. Now a brief words about SFI. SFI is the company that represents RapidMiner in Taiwan since 2017 and providing local support as well as professional services. Actually, it has represented many popular software tools more than 30 years now in Taiwan and helped many of the customers in digital transformation initiatives. Again, thank you very much for attending. Bye-bye.